In this video, we're going to talk about bond polarity. So we've drawn our Lewis structures, we've started to see shapes. We have to use these two to talk about how polar a molecule is. By what we mean there is the charge that attracts that molecule to another molecule. When I have magnets, and there's a plus end and a minus end, and you bring up another magnet, well, the plus end is going to be attracted to the minus end. And those magnets are going to draw towards each other. Well, electrons and protons and distributions of charges on atoms are made from positives and negatives. When I have two equivalent atoms, say two hydrogens, they are both pulling on those electrons, but they pull equally. Imagine a tug of war with two people, equal footing, equal strength. It doesn't really go anywhere. We draw the electrons kind of as a diffuse cloud. Their orbital shape is spread out, and if you are equally pulling, then you are equally spread out on both. And so any equivalent atoms are always going to have an even spread for their electrons that they're sharing. But what happens when you have atoms that aren't equal? What happens when you have a carbon and an oxygen, or a carbon and a fluorine? Well, oxygen has a higher electronegativity. It's 3.5, where carbon is 2.5. Oxygen wants that electron more. Net result is it's kind of like squishing a balloon. If you squeeze one side, the material is going to flow to the other. And so while equivalent atoms share equally, unequivalent atoms will skew towards the side that is more electronegative. And the bigger the difference, the bigger that skewing is going to be. Fluorine at 4.0 is just all the more electronegative than oxygen, and so it pulls even harder. If you take this to the extreme, you have a sodium and you have a fluorine, they don't really form a bond because that electron just completely moves over to fluorine. When you are evenly shared, you have exactly as much of the electron as you're supposed to, but as you start to skew it, you get more and more towards looking like ionic. And so when we start to push to one side, the result is there's just more electrons over there than there ought to be if we were trying to be equal. The more we pile electrons up on the more electronegative atom, the closer it looks to being fully stolen and therefore fully negative. If we've only skewed it a little, then it's only partially negative. And so what we see, this little delta symbol, is we see the partial negative out on the oxygen. Well, if sodium loses its electron, it becomes positive. So as carbon is losing it, it becomes partially positive. These are not full charges like ions because it hasn't actually stolen the electron, but it is unequal. And the more unequal, the more those partial charges appear. This means that you have a permanent dipole. So dipole, two-pole, positive and negative end. You have a permanent charge, even if it's not a full charge, sitting on those atoms. Well, charges can be attracted. And so when you have things like, let's say, CH3F, reasonably negative, reasonably positive, if you have another CH3F rolling by, well, opposite charges can attract. They're not forming bonds in the covalent sense. We're not sharing electrons between those two molecules, but just by being somewhat negative and somewhat positive in those parts of the molecule, those two molecules can be attracted to each other. If I was free floating and I wouldn't do anything as I got close, well, the moment those opposite charges start to see each other, they'll pull towards each other. Now they can only get so close before their electron clouds kind of push off of each other. So there's a balancing, but much like covalent attraction, there's a best distance. These dipole-dipole attractions also have a best distance, and that is closer than floating free past each other. They draw each other in. This is why certain molecules are far more attracted to each other than other molecules. If you have something like CH4, well, CH4 is a gas. It's a gas at room temp. It's a gas unless you get down to incredibly low, negative multi-hundred degrees Celsius. Methane is a gas. And yet, simply by changing to oxygen and having less hydrogens, the mass is almost identical. 16 versus 18. That is not a huge change. And yet water is liquid at room temp. Why the difference? Well, methane, CH, does not have a significant difference in electronegativity. It's a 0.4 difference. And we'll talk about what differences apply, but that's not enough. A CH bond is nearly equally shared. As a result, there aren't charges on methane. If you have a second methane nearby, there's nothing really drawing that methane towards the other methane. And so when they drift past, they just keep drifting. But water, on the other hand, well, an OH bond, oxygen's far more electronegative. So there's a big negative on that oxygen and some pretty big positives on those hydrogens. That result is if another water comes by, well, there's an attractive force between the water and the hydrogens. And so they're able to pull towards each other. So while the methanes just drift past each other because they lack these dipoles, water will absolutely draw towards each other because they do have these dipoles. And so the differences in electronegativity of a bond affects how big of a dipole you have, or if you have one, and introduces the ability for one molecule to be attracted to another molecule with a dipole-dipole attraction.